Thank you so much. I'm very excited to be here. And I'm from Dr. Olan Rawadu's lab, and I'm from the University of Washington. I'm excited to share with you the work that we have done to create an enzymatic assay with lateral flow readout to measure specifically tenofovir diphosphate. And for conflict of interest, we have a couple of patents. So we know that high adherence and maintaining this high adherence is really important, especially to minimize the risk of HIV acquisition and incidence rates, especially for people on PrEP in blue here. And we also know that maintaining adequate adherence is important for people living with HIV to maintain this viral suppression and to achieve U equals U. And one strategy for adherence is to provide drug level feedback. So in many recent studies, we've shown that people have shown that drug level feedback, especially objective measures, are important to help improve retention and also motivations for individuals taking antiretrovirals, and also provide additional information for clinicians. However, the gold standard continues to still be LCMS, which, while incredibly sensitive and quantitative, also has a high time and cost burden, which makes it a centralized and also difficult turnaround times. For example, this study by Roberts et al. Demonstrated a 60-day delay, which makes same-day or real-time or same-visit feedback difficult. Recently, in the past few years, Dr. Monica Gandhi's group has developed this tenofovir measurement using urine lateral flow tests that have been able to demonstrate high correlation with LCMS measurements, and also correctly identified participants who took tenofovir within the past 24 hours. And there's many advantages to this in the case where it is incredibly inexpensive and fast to run, which makes it scalable. And it is also a very familiar format, as it has 2 pregnancy tests, which are already taken and is easily integratable and an easy matrix to collect. However, because this is measuring tenofovir, which has an incredibly short half-life, it also makes it very susceptible to white coat adherence. So if we look at the active intracellular form, if we look at tenofovir diphosphate found in red blood cells, it has a much longer half-life of 17 days and is a better marker for cumulative adherence, which it can usually indicate between 1 and 3 month adherence. And so we wanted to set out and ask, can we measure this long-term indicator with the ease and usability of lateral flow assays? And we set out to do this with an enzymatic assay. Previously, we have been able to measure the presence of NRTIs, specifically in here, tenofovir diphosphate, in blood samples, where when we combine it with DNA synthesis reagents such as DNA template, primer, nucleotides, and HIV-RT, we're able to back calculate the concentrations of tenofovir diphosphate based off of this DNA chain termination activity. And we also demonstrated high correlation with LCMS results in 74 clinical samples. And at this moderate threshold, we were also able to demonstrate high sensitivity and specificity. We're not the first people to do this. We've also, many people have measured antiretrovirals with enzymatic assays. However, these were measured in PBMCs, which are a more difficult matrix to collect, and also utilize radiolabeled DNA. But now that we are in the age of DNA prevalence and the accessibility of CRISPR, we have recently developed the reverse transcriptase activity with CRISPR assay or reactor, which Willow also talked about yesterday in their presentation. And this harnesses the collateral cleavage activity of Cas12a specifically, where the template has an additional Cas binding region that when double-strand DNA is synthesized, it will bind to Cas12a, it will create a conformal change, and this Cas12a will begin collateral cleavage. Here, with a fluorescent reporter, we can measure fluorescence and additionally, while this is a step towards decentralization of this technology and this enzymatic assay compared to LCMS, in order to further integrate within clinical settings that have, and to be able to be readily available in these different like existing infrastructure, we can further minimize the need for external equipment, especially for readout. So instead of a fluorescence reader, we asked, can we do lateral flow detection and colorimetric detection? And the way that we can do this, and we can achieve this by switching out our fluorescent reporter with a biotinylated reporter. And this reporter allows us to do lateral flow detection, and I will provide 2 examples of the 2 ways this can go, essentially, with readout. So in the presence of high NRTIs, so in high drug, our DNA synthesis is likely to be terminated early on. This means that our Cas12a enzyme is unlikely to be activated, in which case our reporter remains intact. When it is absorbed by our lateral flow assay, the reporter will bind to neutravidin, which is what will give us a colorimetric change and produce a strong test signal. This will be captured by our test line of our lateral flow assay, in which case this will produce a distinct 2 lines on our lateral flow strip. Conversely, if we look at the low tenofovir diphosphate concentrations, DNA synthesis is unlikely to be inhibited, so we'll see a lot of double-stranded DNA. This also will activate our Cas enzymes, in which case collateral cleavage will occur, so everything will be chewed up, and our reporters, when absorbed by our lateral flow strip, do not produce a colorimetric change, and we see the presence of only 1 test line. So this difference between this 1 and 2 test line is our basis of our enzymatic assay with lateral flow readout, and we were able to demonstrate this in both buffer and spiked blood. In the spiked blood, we had blood from individuals not taking any antiretrovirals, and we added known concentrations of tenofovir diphosphate to characterize and tune our enzymatic assay. Specifically, we were able to see that on the x-axis, we have increasing concentrations of tenofovir as we go to the right. And then on the y-axis, we have signal to background ratio, which indicates the test line intensity of our lateral flow strips. So on the bottom of the graph, I have provided representative images of what these look like. And in our no TFV-DP concentration, we see just 1 test line. However, as we increase our tenofovir concentrations, we'll see the presence of stronger and stronger test lines, which is reflected in our signal to background ratio. And so through this, we were able to identify several key components to our enzymatic assay that can help us tune this and to adjust it for different thresholds, including incubation time, which essentially lets our Cas enzyme more or less time to cleave, and also DNA reagent concentrations, as it gives our NRTI time and balance to be more or less competitive in our enzymatic assay. We were fortunate enough to receive 30 samples from Dr. Kenneth Mugwanya and did a lateral flow reactor pilot clinical validation, where we saw high correlation with LCMS results that were taken from the clinical pharmacology lab. And specifically at this moderate threshold of around 700 femtomoles per punch, we were also able to see high sensitivity and specificity. And so we are very excited to continue doing clinical validation and to incorporate more, and to look at different thresholds. And we're also interested in looking into future work, which includes integrating these simplified blood collection devices, which will allow us to have we hope to integrate commercially available blood collection and sample preparation devices to make the assay upstream a little bit easier, and also to lean on Dr. Olan Rawaju's 3D printed microfluidics expertise to potentially put this enzymatic assay on a chip and to automate the liquid handling steps or create some sort of multiplexing ability. And I would like to thank you for your time, and all the people that have been a part of this project. Thank you.